Hello, this is a warning to tell you that in what follows I systematically mispronounce the word decay. I pronounce it incorrectly as decay, as many people do, and I'm very sorry about that. So this is just a notice for you to understand that it should be pronounced correctly as decay. Look here.
Decay.
Decay.
Okay, so you heard both British and American pronunciation. So try to pronounce it correctly and try to ignore my mispronunciation. Example of exponential decay. When a diesel electric generator is switched off, the current dies away according to the formula, and here we have a formula. I of t equals as 24 times 0.25 to the power of t amps. Amps, it means amperes, where t is the time in seconds after the power is cut. Find I of t when t equals 0, 1, 2, and 3, etc. Okay, so let us start with part A here. Let me copy the formula to start with. So I of t equals 24 times 0.25 to the power of t. Okay, so if I want to find the current, the electric current at these times, I have to substitute the values of t to this formula. So I of 0. So the current at the moment when time is 0 is 24 times 0.25 to the power of 0, which is, since everything to the power of 0 is just 1, so it must be 24 amps. It's like amperes. This is the unit of current, and in Slovak curriculum you use this symbol A for ampere. Okay, so 24 amps. I of 1, so the current at the time of 1 is 24 times 0.25 to the power of 1, so it's just 24 times 0.25. So 24 times 0.25 is 1/4 of 24, it's 6. So we have 6 amps at the time of 1. Whatever unit we use, maybe it's millisecond or something, I don't know, or seconds maybe. I of 2 would be 24 times 0.25 to the power of 2. We have to calculate that, so 0.25 to the power of 2 is 1/16, and this times 24 gives you 3/2 or 1.5 amps, like this. And finally, the current at time 3 is 24 times 0.25 to the power of 3, and again let me use the calculator. So 0.25 to the power of 3 is 1/64, and this multiplied by 24 is 3/8, so it's 0.375 amps. Okay, so we have completed part A like that. In part B, what current flowed in the generator at the instant when it was switched off? Well, when it was switched off, the time was 0, so for t equals 0, I should get I of 0, which is 24 amps. Okay, so here what we have here is a transient phenomenon, something what happens to the electric circuit when you switch it off and when you cut the power, and actually the formula describes this phenomenon completely, so it tells you what is the time dependence of current, and using the formula you can easily find the current at time 0, which means that this is in the beginning when the power was cut. Now in part C we have to plot the graph of I of t for t which is greater than or equal to 0 using the information above. Okay, so we have the formula, we have everything. Then let's move to GeoGebra. So this is the GeoGebra again. Let me choose the spreadsheet view. I will add it here, and again take time to change from 0, and I don't remember for greater than 0, 4 times greater than 0. So we have to do it for times greater than 0. Let me do it for the first 3 or 4 units. So 1, 2, 3, 4, let me go to 5. Okay, like that. Now here I should have the formula. So the formula is 24 times, and then there was this 0.25 as a base, which is raised to the power of the time, which is a1 in this case, like that, and we can copy it down to obtain the answers. So these are the answers that we obtained from in part A. So 24, 6, 1.5, 0.38, actually it was 375, but this is rounded up like this, rounded off, sorry. So these are the currents, and we have to show the graph. So let me include these as points. So I will create a list of points, and these are included here. And now let me zoom to fit. So here we are, 24 as the initial value, and here are the decreasing values of current. Now I can also plot the function of I, so it's going to be y equals 24 times 0.25 to the power of x, like this. And this is the function. Actually, what I need in this exercise is only the part of this function, the part represented by non-negative values of time. So I should ignore this part to the left from the vertical axis. So this is the function representing the decay of the current, the way in which the current decreases exponentially in time. Okay, now the last part, and this is very interesting. Use your graph or technology to find how long it takes for the current to reach 4 amps. Okay, so we know that 4 amps is reached sometimes between 1 and 2, because the current at the time 1 was 6 amps and at 2 it was 1.5, and it decreases. So somewhere in between these two times there should be the value of the current corresponding to 4 amps. So let me use the graph, look at this graph, and I need to find when it reaches 4 amps. So 4 is here, and I need the intersection, this point in the graph. To do it, what I do, I include another line, y equals 4, to this graph. I have it here, and now let me construct a point at the intersection here, at the intersection of these two curves. So this point here, this is the intersection, and I will choose settings, and I want to show not only the name but the value of this. So yeah, here it is. I can close this. So this point has the coordinates. The horizontal coordinate is 1.29 and the vertical one is 4. So it tells me that at time 1.29 units the current reaches the value of 4 amps. So the answer is t equals 1.29. So for part D, I have the answer obtained from the graph that t should be 1.29. Well, this is actually just approximate answer, and therefore let me use this symbol to write it down. So this concludes this exercise.